All right, everybody. Thanks for coming. We'll go ahead and get started in the interest of time. So my name is Matt Robinson. I am the ROS Industrial Consortium Americas kind of program manager. So anyway, I wanted to touch on a bit of an introduction. So thanks for coming to the ROS Industrial Developers meeting. Michael, I see his camera's on. So my name is, as I said, Matt Robinson. I'm down here at Southwest Research Institute in San Antonio, Texas. We steward the ROS Industrial Consortium Americas out of here. And obviously, there's been a long history of supporting open source for industry here. But I want to take a moment today to introduce Michael Ripperger. He is stepping in and taking over our ROS Industrial Americas technical lead role, which was formerly held by Levi Armstrong. So welcome, Michael. And Michael, thank you for stepping into that role. And Michael was going to talk a little bit about the Descartes Light work that was shared at a community meeting, but like some work that's going on to kind of like, hey, how do we, and some opportunities to potentially refine it further and how it works and how we're using it today. And then following that, Ben Greenberg is going to share with us some work he did using the Tesseract motion framework to experiment with human-robot interaction. And then finally, I'll take a little bit of a moment just to remind this audience about work going on the hardware interface working group, which is official ROS-II working group. And so some opportunities there to engage as it's meeting right now every other week. And of course, then we'll look and solicit some feedback on how to make this time as most value added to you and your organizations as we can, and how to foster like effective collaboration where it makes sense. So without further ado, Michael, you want to say a few words since I put you on the spot?
Yeah, sure. I guess I can introduce myself real quick. Like Matt said, my name is Michael Ripperger. I work here at Southwest Research Institute. I've been here for about 7.5 years. I've been doing ROS development for about 5 of those years. So I'm a maintainer and active developer on several of our ROS industrial repositories. So like Matt said, I'm kind of stepping into Levi's role here as the consortium kind of technical lead for America. So happy to be here, looking to kind of excited about being more engaged with the community and yeah, kind of actively continuing our development on some of the tools that we have in the ROS industrial organization. So yeah. Cool. So I guess with that, I can kind of jump into this little short talk about some improvements that we've been making to the Descartes motion planner. So let me see if I can share my screen here. Can you guys see this presentation? Should be like a PowerPoint type thing.
Yep. Yeah, looks good.
Awesome. Cool. Okay, so I'm kind of repurposing one of our colleagues' work here, but anyway, so as a background, for those of you who don't know, we have several different motion planners that are part of the ROS Industrial project, and one of them is called Descartes. It's been around, I guess, ever since I've been at SWRI, so I think it's probably 6 or 7 years old. But the idea behind Descartes is a motion planner for kind of sequences of waypoints, and typically Cartesian waypoints. That's kind of where the name comes from. But essentially, the sort of planning that we're looking at doing is more or less kind of what's shown in this picture here. I guess I think I'm stuck on the wrong screen here. But anyway, so we not only have tool paths of Cartesian waypoints, and it's not just point-to-point moves, but it's moves between a sequence of defined waypoints. That's kind of Descartes' bread and butter is taking those and turning that into a graph search problem and finding the optimal solution from as many samples as we can get that represent valid IK solutions for each of these points in a waypoint. So I guess some history about Descartes. I think originally it was based off of Boost Graph library and was ultimately migrated to kind of a custom dynamic programming type search algorithm. And so recently we've been using this planner with kind of robotic systems that have lots of degrees of freedom. And so we're running into a lot of memory constraints with sampling and things that our problem was kind of growing too large for the computers that we were using to solve them. So we kind of launched this project to kind of look at different ways of setting up that graph search problem to be a little bit smaller and more easily represented on kind of a standard computer where you don't have to have tons and tons of memory to be able to like represent and solve these problems. So nominally, that's kind of the limitation of what we're running into with Descartes. And so, you know, over the last couple of years, we've taken the Descartes repository that exists in the ROS Industrial repository and kind of refactored it into kind of a more modular structure in the Surrey Robotics organization that we are calling Descartes Lite. A little bit of a misnomer. It's not really that much lighter weight than regular Descartes, but it's a more flexible implementation. So that's kind of where we focus most of our development efforts, was on this new Descartes Lite library. Yeah, so kind of going into this a little bit more, right? So we're motion planning. We're trying to take these target Cartesian positions, these like waypoints that we want to go to, and then we want to sample for each one of them all of the different valid IK solutions that there might be. So if you kind of think about an under-constrained process where you don't necessarily care about tool orientation, there's kind of an infinite number of ways that you can reach this waypoint. And kind of similarly, if you have a robot on a gantry or a robot on a rail, the robot can be at a lot of discrete positions on that gantry and still kind of be at the target waypoint that you want. So essentially, that's kind of what each rung in this graph here represents, is the number of valid samples that there are for that particular waypoint. We're trying to find the optimal path through each one of those that kind of accomplishes our tool path. So yeah, like I mentioned, kind of the main problem with this approach when you're generating this fully connected graph where you have tens of thousands or millions of waypoints and, you know, in squared connections between them, that your memory footprint just grows exponentially. And so you can quickly run out of RAM on your computer to be able to solve this if you're generating the entire fully connected graph. And so kind of the way that we were getting around that was trying to sample less, which is not quite as ideal because you don't get quite as close to the optimum solution when you do that. You know, sometimes we would buy these giant computers that had tons and tons of RAM so we could make our problems a little bit bigger, and that kind of gets expensive and seems a little bit unnecessary. Yeah, so nominally what we were trying to do is leverage kind of some of those existing graph search algorithms from Boost Graph Library again, and try to implement them in a way that we didn't actually need to have kind of a fully connected graph, that we could be dynamically generating these graphs and hopefully having a smaller memory footprint. So that was kind of one of the big parts of restructuring Descartes, was to be able to support multiple different types of graph search algorithms under the hood. So you kind of pick and choose depending on what you're more interested in, right? So like the implementation we have right now is really, really fast, but doesn't scale well with memory. And so that's kind of the idea of putting some different backends that are based on Boost Graph libraries, that they're a little bit slower in runtime wise, but can be a little bit more memory efficient. And then we get access to a lot of existing kind of tested graph search algorithms like A-star and Dijkstra and a few other things as well. So basically, we kind of put together a couple of different search algorithms on the back end and tried to kind of benchmark them against each other. And so nominally, we implemented kind of the fully connected version of a Dijkstra search. And then we also kind of, after we did that, created this dynamic graph construction search algorithm where we kind of go rung by rung and evaluate each, you know, all the different samples, but then only take kind of the best, you know, head of that graph search and expand it to the next one to try to limit the number of connections that we actually made. And so I think from some of our benchmarking and testing that we found that it consumes a significantly less amount of memory. And so that lets us kind of build our problems as big as we want them to be and sample kind of as finely as we want to, with being able to use significantly less memory, which is a huge plus. So we have a couple that we actually implemented out there. I think most of them are kind of modified versions of Dijkstra, things that kind of run Dijkstra as a whole on a fully connected graph, and then do this kind of dynamic connections using Dijkstra as well. And then I think we have a couple, I think we also implemented like some depth first searches as well for use cases where maybe you just want to find some solution very quickly, but you don't necessarily care so much that it's an optimal solution. So a lot of times in our applications, we are using Descartes as kind of a first step in a pipeline. So we use Descartes to kind of get a good guess at what an optimal or close to optimal solution might be, and then use a different planner like TrajOpt after the fact to smooth it and make it more optimal in kind of a more traditional like mathematical sense. So we have a couple of different planners there for various use cases that have been merged in. So we also, as a part of this project where we're improving Descartes, we also kind of looked into leveraging the search algorithms that are in OMPL for kind of searching our connected graph. So that's still a bit of a work in progress, but we were kind of excited about trying something like that and getting maybe more of like a randomized sort of search that potentially could be even faster than the kind of Dijkstra search. Again, in cases where you're not really needing an actually optimal solution, but you want something fast and you maybe want a lot of different solutions that you could kind of provide as seeds to optimizing motion planners or something else. So yeah, so kind of going back, I think these changes obviously are helpful for us because we work in a lot of spaces where we have underdefined processes and are working with, robotics that have maybe many extra degrees of freedom. So I think in the future, we kind of are looking at deploying these for like gantry and linear rail-based systems or systems with external axes. So maybe you have a 6-DOF robot and a 2 or 3 axis part positioner. So you can use Descartes to kind of sample all the valid ways that you can get your robot to go do something with all these extra degrees of freedom. And then we also kind of work a lot in the areas of under constrained processes, like painting or sanding, where maybe the tool orientation doesn't matter. And we want to be able to kind of sample around that and find the robot configuration that works the best, kind of throughout our tool path and be able to like leverage that flexibility. So I think that's kind of the huge value add of Descartes is being able to kind of explore this space and come up with a trajectory that's significantly better than if you were just kind of going exactly to the one waypoint solution that maybe you've sampled. And so I think these changes really enable you to kind of be able to sample those extra degrees of freedom a lot more finely to generate a solution that gets a lot closer to an optimal solution. Yeah, so still kind of a work in progress. I think kind of generally the Descartes library, this like Descartes library that's on Swery Robotics organization, ultimately we'd like to migrate that back over to the ROS Industrial repository and kind of replace the old version of Descartes that's out there. So I think those are some future goals that we have, and then doing kind of a reintegration with MoveIt as well. So Descartes Lite is kind of just a pure CMake library right now, and so we've kind of integrated that into the Tesseract planning framework. But then, obviously we're still interested in supporting MoveIt. So I think that's something that we've got on our horizon is looking at how we reintegrate this with MoveIt as well. So I think that's pretty much all that I had to share about this. Happy to take any questions that you guys might have, or we can table them for later.
Hey,
yeah,
Michael, does your Descartes Lite work support both ROS-I and ROS-II?
Yes, it does. So because it's pure CMake, it's just ROS agnostic. So we've deployed it both with ROS-I and ROS-II systems. So it's seems to be a bit of a strategy as well that we're taking with some repositories that don't necessarily have, a strong need to be like fully integrated into the ROS ecosystem. It's kind of making them pure CMake and then putting the kind of light ROS wrappers around them to integrate them with the like ROS ecosystem. Yeah.
And then you mentioned, this is Matt, by the way, sorry, Michael. You mentioned the migration out of Swery Robotics over to ROS Industrial. In your mind, like, what is the gateway to kind of, so to speak, it's ready to go to ROS Industrial? I mean, what in your mind makes it sort of ready to move over there?
Yeah, I mean, I think nominally the Descartes library now has more unit testing than Descartes. So I think there's probably a little bit of work that we do there to kind of like fully flesh that out and make sure that we kind of capture as many bugs as we can before we do that migration. I think there's maybe like another small structural change we might want to make in terms of like where an interface lives and how it gets accessed. So I think we probably make that change before we move it over. and then, yeah, maybe kind of take one last pass at it and make sure it's got all the same functionality that we have in the current Descartes library before kind of, tagging that and replacing what's out there with this new version. But yeah, but not only, I think the idea is that it's more flexible in terms of like what backends that you can use and how you can configure it than kind of the current Descartes. So I think it's generally kind of an improvement over what's out there. But yeah. Sweet.
Any other questions for Michael?
Looks like John posted in the chat as well that Descartes Lite has been provided in a Conda environment as well, so you can download it there, which is pretty cool.
Michael, can you comment on the usability of Descartes Lite compared to the older version of Descartes?
Yeah, I've used both of them in different projects. I mean, I think being a developer, it's easy for me to say that it's very usable because I understand the interfaces. So, I mean, I think to Matt's point, there's probably a little bit more work that we can do on the documentation side before we try to migrate it over and say like, hey, this is like really ready for everybody to use, because I think kind of the concept of Descartes it's not always like very straightforward. So I think there's some pretty low hanging fruit that we can take there as far as like putting out like a couple docs pages and then running the like Doxygen and writing something that's kind of explains what's out there. But yeah, kind of like I've been saying, I think the overall structure is a little bit more flexible, so you can choose like how nodes get evaluated and how connections get made a little bit more easily than you can in the current Descartes library. And the current Descartes library is fairly tied to move it as well. So if you wanted to use it in a different framework like Tesseract, it's just not really possible. And so I think that's kind of another improvement on usability is, if you don't even want to tie it to ROS, if you've got your own way of kind of structuring a motion planning problem that Descartes is good for, then you don't really even have to use ROS or Tesseract or move it. You can use kind of Descartes for itself. So I think just kind of generally being agnostic of ROS and things like that makes it slightly easier to use.
No, thanks, Michael. It's pretty
Cool.
interesting. Any other questions, final wrap-up questions for Michael?
Yeah, this is John Watson. Just want to mention that I think that you can access Descartes using Python now from Tesseract. I haven't tried it though directly, but I think you should be able to.
Oh, cool. Yeah, I have not used the kind of Tesseract Python interface, but that's something that I know you've been working a lot on, and I'd definitely be interested in kind of testing that out in the future. So
yeah,
awesome. Good to know.
That's taking the high-level Tesseract interface rather than the API from Descartes. So I'm not exactly sure how that would look.
Yeah.
I wanted to ask as a question, how do you pick which planner to use now? So there's Descartes, the OMPL libraries, and the TradJob. So, which planner do you use for what task is not always clear at this point.
Yeah. So I think it definitely is application specific. So I think the only reason I would ever use Descartes is if you have like a toolpath with more than 2 waypoints. So Descartes is not a kind of point-to-point motion planner. Like it's not capable of really doing anything in between the waypoints that you give it, like OMPL is, right? So if you do a point-to-point move with OMPL, it'll generate a bunch of states to make sure that your robot moves out of collision. But Descartes doesn't do that. All Descartes does is essentially sample the valid IK solutions at each point in your toolpath and then try to figure out which configurations it should choose at each one to kind of fill out that toolpath. So I would say like the real use case for Descartes is if you have some sort of toolpath with multiple waypoints, either joint waypoints or Cartesian waypoints. So I think Descartes is really great for that, and especially if you have extra degrees of freedom because your process is under constrained, or you have 7 or 8 degrees of freedom in your robot system or more, and you want to sample those, and you don't want to just kind of fix those joints and then do a fixed IK solution. So I think that's kind of the use case of Descartes is extra degrees of freedom and toolpaths with multiple waypoints. I say OMPL, I think is probably more generally reliable than TradJops in terms of like being able to find a path between kind of point-to-point motion. So I think that's kind of the bread and butter of OMPL is doing point-to-point motion where you don't necessarily care what happens in your trajectory in between. You know, there's some things you can do to kind of control that, but generally that's kind of the idea with OMPL. But I think because it's kind of random search based, you can get a lot of crazy looking trajectories that, you know, maybe you're not really ideal, or maybe you're not necessarily comfortable executing, or you don't, they're technically collision free, but they can kind of look a little bit odd. And so then I think that's becomes the bread and butter of TradOpt at that point, is to take a trajectory, and then you can define a lot of optimization criteria, like keep me as far away from collision as possible, smooth the velocities and accelerations and jerk of this trajectory, trying to make those as minimal as possible, try to avoid Cartesian singularity. You can define a lot of those constraints with TradOpt, and you can give it a trajectory and say, okay, take this trajectory and optimize it for these criteria that I care about. So, if you use TradOpt generally for just kind of a point-to-point motion, and you don't give it a decent seed, sometimes it has a really hard time converging. And so that's kind of what I mean by being slightly less reliable than OMPL for just kind of straight point-to-point moves. So typically what we do is we set up these pipelines of planners. So for kind of like a toolpath type motion plan, we'll run Descartes first, and sometimes we'll do it relatively sparsely. And so what that gives us is kind of a trajectory that's somewhat optimal. It's close to the optimal solution, but not exactly there, but it's a good starting point for TradOpt. And especially if we have under constrained processes or lots of extra degrees of freedom, we kind of narrow down our space about where those extra joints, like what their positions ought to be. And then we'll pass that to TradOpt and say, TradOpt, okay, take that and then actually optimize that into a much better, more optimal trajectory. And then, for free space plans, we'll kind of do the same thing, where we'll maybe try the TradOpt plan first. And if it fails, then we'll say, okay, well, let's run it through OMPL. OMPL will probably give us a solution. And then we'll run it back through TradOpt after that to say, okay, if OMPL gave us a solution, let's run it through TradOpt and try to make it significantly better. So a lot of times we're not using these planners just by themselves. We're using them kind of in combination with each other. And so that's a lot of the work that we've been doing on the kind of Tesseract process managers package, is kind of setting up task flows where you can say, do Descartes, smooth it with TradOpt, do collision checking and spline, and time parameterization after the fact. And then, so that's kind of been set up to where you can kind of plug and play like your own pipelines of planners to kind of meet your needs. But yeah, I feel like I talked a long time there. Did that address your question?
Yeah, I think it's an interesting problem. So I've actually been tinkering with the free space planner, and what's weird is OMPL does switch configurations randomly if you plan the same plan over and over again. So I'm actually interested now to know if you can actually go from OMPL to Descartes and then to TradOpt to try to get rid of that. I don't know.
Yeah, I never really thought about that, but yeah, I think OMPL essentially would give you a bunch of joint waypoints. So I guess the tough thing there might be, Descartes essentially samples waypoints and generates a whole bunch of valid joint states for like a Cartesian state. So if OMPL is spitting out Cartesian states, then that's probably possible. But if it's just spitting out kind of joint configurations, there's not really any way to sample that into multiple options unless there's something special about your application where you can do that. But if you can do that, then definitely that would be possible. But I don't think we've ever necessarily tried anything like that. But
all right. Well, cool. Great discussion. Obviously, there's still probably a lot of both guidance, and we're taking under consideration, we had created a sort of this pipeline advanced topic with when TradOpt was first introduced and Tesseract came out. It's definitely something on our horizon to bring back via the training as well, to give people a little bit more under the hood views of how some of these tools work in practice under sort of like a guided training environment, right? So stay tuned as we continue our journey of refining the training around ROS-I in particular. It gives us that opportunity to refresh a lot of that training content. If this is sort of like an area of interest from the community, obviously we're all ears. So feel free to provide that sort of, if additional resources on this topic are helpful, let us know.
Yeah.
I think Michael, with that said, we should probably introduce Ben. Ben, are
Yeah.
you still online and able to chat for a little bit?
I'm online. I'm ready to chat. I'm ready to party. Let's do this thing.
Ben's always ready. I appreciate it. So Ben Greenberg is one of the developers here, also at Southwest Research Institute. He had the opportunity to leverage, do some work in Tesseract to facilitate some human-robot interaction capability. So Ben's going to share some of that work. Ben, the floor is yours.
Thank you, Matt. Trying to share my screen. Hopefully someone hollers if it's not showing up.
You look good.
Great. So yes, I'm Ben Greenberg. I too work at Southwest Research Institute. And recently I had the opportunity to do some research into human-robot collaboration, which is sort of a passion area of mine. And we were able to do this leveraging many of the tools in the ROS industrial ecosystem. So I'll sort of give a run through of what the motivation and goals of this project were, as well as some of the approaches that we took to achieve it. And then I'll show some videos that I think are cool at the end. So let's see. These slides will move. Okay. Yeah. I don't know. This is going to be a short enough talk. I don't know why I really put an agenda in here, but we're going to talk about what we're doing, why we're doing it, what we did, and what we want to do in the future. So to get to the core of the problem that we're trying to solve is to think about what human-robot collaboration aims to do, and that is to leverage the differing skills of people and robots. You know, we commonly use robots for those repetitive, boring, dangerous jobs, and they're really good at those. But where they fall short is in jobs that require really fine sort of dexterity or complex decision-making or creativity, which are areas that people are very good at and can do things with great ease that robots couldn't hope to do, you know, in a million years. So a lot of applications, whether they be assembly or refinishing or any number of things, would really benefit from leveraging both of these skill sets simultaneously. Sort of imagine a robot hands a part to a person and the person does the assembly, sort of that spirit. But the current technology that we have in robotics and in perception doesn't really support this out of the box very easily. So the goal of this project was to enable that richer interaction between humans and robots by giving the robots a more sort of intelligent perspective on their environment, and sort of hinting as to what that is with the image on the right, which shows our motion capture system, which was the perception element of the system, you know, figuring out where a person is in the work cell, and you know, ultimately we're able to relate that to the robot planning environment. So I'll walk through my fun stick figure scenario to illustrate the problem and end goal a little bit more visually. So say we've got this robot that needs to get something off this shelf and move it to the table. That's great. We're all happy. That's what we want robots to do. And when this person is standing at this distance from the table, that robot can plan any motion using OMPL, TradgeOpt, whatever flavor you like. And that's great. The problem is if a person is working at the table or getting in the way of the robot in some other manner, all of a sudden this trajectory, which the robot had planned to be safe and free of collisions, is now going to hit the person. And that's a bad thing for a lot of obvious reasons, safety primarily, but also productivity. The robot bumps into a person, that can cause a stoppage in work and robot downtime, which, you know, any time that the robot's not moving, you're sort of losing money with it. So we want to keep robots moving safely and continuously. What we want the robot to do is to recognize that a person is in its way and change its motion on the fly to avoid the person while still getting its job done. So the way that we're doing this from very high level is adding this perception system which is able to detect where a person is in the environment and monitor that in real time, and then feed that into an intelligent motion planner. And the pieces of all of this are either ROS built or integrated with ROS. So this intelligent planner is really another word for using the Tesseract TradgeOpt motion planning pipeline that Michael was just discussing. So using these two systems in tandem, we're able to recognize when a person, or not we, the robot is autonomously able to recognize when a person gets in its way and is able to quickly and effectively change its motion to avoid the person. So to talk a little bit more about the motion planning system and improvements that we made to achieve this project. So as I mentioned, we have this pipeline of Tesseract, which is providing our environment monitoring, as well as some of the basic motion planning, that OMPL interface. And then we're feeding it into TradgeOpt to change that motion plan once it's been developed. And those changes are necessary to respond to changes in the environment. Because recall that the person is being monitored in real time, and as they're moving around, the environment in which the robot has to plan in is changing. So what might have previously been a valid collision-free path may not be still valid a few seconds later once a person is moved. So we need that TradgeOpt planner to be running continuously to update itself or update its plan based on the changes in its environment. We're able to do this because of recent changes to the TradgeOpt pipeline using the IFOP library, which is another optimization library that I won't pretend to know too much about. But what I was able to do was use these tools which have been developed and feed forward a few improvements to it that I'll touch on in a second. But using the system, we're able to tell the robot that we need you to continually be checking whether you're in collision or not, and whether your planned trajectory is in collision, and then update that plan once you find a new one. So we had hoped that the planner would be able to run it at least 50 Hertz, which is evaluate whether its trajectory is valid and update it 50 times per second. And it's worth noting that each update is not necessarily a new valid plan. It's just a step closer to a valid one. So this is still an area of sort of research that we're doing, is how to ensure a safe motion in a certain number of iterations or a certain amount of time. But we have other fallbacks in case a new plan isn't developed in time. So some of the improvements that we made over the course of this project, and I saw that Levi's online, so I'll give a shout out to him because he did a lot of this work with us, was to develop, a big area of development was in integrating continuous collision checking, which is necessary for robot motions that are planned initially with several discrete steps along the way. And the way the planner works is that you solve each of those discrete steps, and if those are collision-free and satisfy all the constraints you've defined, then your motion plan is considered valid. However, that's a problem if in between those states, there's a motion that passes through an invalid state, like a collision. So we implemented this continuous collision checking system, which is able to evaluate all the the swept motion between the discrete positions to ensure that there are no sneaky sort of failures to meet the constraints that we've met in between the defined positions. Another thing that we did was add this acceleration constraint, which is another way to smooth motion by minimizing acceleration between the acceleration of the robot joints as it's moving through its trajectory. And then all of these changes are integrated into the online planning example, which is a useful example for this sort of real-time motion planning that exists on the TradgeOpt repository. And it's a useful place to look. And I spent a lot of time looking at that to template the way that we're going to develop this system. So all these changes have been pushed back up to the upstream repositories and are available for use. And I'd say that this online planning example is a really good resource to refer to when trying to implement an online planner of your own. So when we did it, we saw a wide range of planning speeds, and this was largely dependent on the computing hardware that we were using. But the system that we ended up working on out in our lab was able to solve, I think the average was about 60 hertz, which was good. However, it's worth pointing out that that average of 60 hertz does not mean that we met our minimum frequency of 50 hertz. So you can see that there were plenty of motion plans that took a lot more time. This lower hertz, more time. So that was a problem that we encountered, in that sometimes the planner would be slower to respond than we wanted it to be. And we're able to resolve that for our purposes by simplifying other parts of the process. But these were our results from the planning speed side of the problem. So the other interesting part of the robot motion pipeline was how to execute these motions once they've been changed, or rather how to execute these plans once they've been changed. So you can see up here, we've got this arc here, motion 1, that's sort of the initially planned trajectory, which we send to the robot and say, start moving. And then at some point in the middle, if a collision is anticipated, the robot planner says, oh, my trajectory 1 is not good anymore, we need to do trajectory 2. And this hatched area over here was a bit of a question mark at the beginning of the project for how to, in real life, transition from one trajectory to another smoothly. And there are other implementations of sort of true trajectory splicing out there that have been integrated with libraries like ROS-Control. However, we were using a robot that did not have that type of interface available. So we had to do something a little bit custom and creative and ultimately effective. And what that was involved actually starting our planning not from the current position of the robot, but from a position where the robot was known to be in a small period of time. And what that allowed us to do was to share a point between trajectory 1 and trajectory 2 that was yet to be executed. And that meant that while we were executing trajectory 1 and planning trajectory 2, we still have a little bit of time to blend these two together. So we didn't have to do any fancy interpolation or smoothing between them, because they shared an exact point in joint space. So there was some question as to whether this would actually work. This was all sort of theoretical, but when we modified the Motoman driver and the industrial core packages, which help send trajectories to it, we were pleased and relieved that it did actually work. So this was found to be a pretty effective way to use the libraries that already exist, and even if they don't have ROS-Control interfaces, just to be able to splice these trajectories together. And I use the word splice sort of loosely. So ultimately, the goal of the project was not just to develop a bunch of software, it was to make some robots move. So as I kind of alluded to, we were able to do it. The robot was able to move through space and adapt as a person got in its way. There were definitely limitations that we encountered in this process, but the packages that were available and the tools that we developed and pushed back out there certainly made this a lot easier than it would be if we were starting from scratch. And I guess maybe before we do future work, I can show some of those videos that I was talking about. So this just shows a little bit of what the motion capture system looks like. And you can see this is running in real time on live data, monitoring the joint positions of me as I'm walking around. And what we actually did was use multiple cameras, which are each doing the same motion capture process, to triangulate each of these joints of the person in 3D space. So once we had that, we were able to convert it into a format that the robot environment was able to use, and then plan around that. And now to look at the robot, oops, that's not going to work. So this first video is just showing, start that again. This first video is just showing how the robot likes to move normally from, this is sort of one of the representative motions that we had it doing, this sort of point A to point B. And obviously it's a very simple motion. And without a person in a way, this is the most efficient way for the robot to execute it. But there is more of a challenge when a person does get in the way. So this is sped up a little bit. So I go stand in the way of the robot, and it just recognizes that I'm in the way and changes its motion without stopping and continues on to its goal position. I'll show it again just because I think it's cool. And then we'll do one more for good measure.
So it looked like, Ben, you were like, not so sure how it's going to move. You were kind of leaning a little bit.
Yeah, no, I was definitely at times not so confident in the system, but definitely built up over time. And let's see if we can get this to show. All right, I'm not going to futz around with that other video for now. But yeah, the system is definitely not like a final sort of factory floor ready system right now. It's definitely more of a research platform that can be continually improved. But we're really pleased that we were able to get even as far as we were, given the, at the beginning of the project, we had this sort of framework and sort of intention for how the system would work. But a lot of things were pretty open-ended and uncertain. In particular, just bringing this real-time motion planning system out of the simulation and into the real world. So even though we were able to do it with a little bit of trepidation, I definitely call a big win. And some places that I'm interested in bringing this research in the future is sort of focusing more on the human side of that human-robot interaction. So what that involves is using this robot cell that we saw in the video as a test bed for testing out human factors and evaluating the sort of psychology of the people that are working next to the robot, because it's all well and good if the robot's able to avoid a person, but if a person is really uncomfortable being around a robot that's able to change its motion on the fly, then it's not really a valuable system. So that's an area of research that is definitely worth exploring further, and this system provides that test bed for doing so. We've also at Southwest Research done some work in predicting motion in our autonomous vehicles group in particular. So you can see here, using a similar motion capture system, we developed a system to sort of anticipate where that person's center of mass will be in a small amount of time. So that's this blue dot over here. And it's not a great leap to see how that could be applied to a system like the one that we were describing earlier. And other areas that would be interesting to do would be to integrate with different robots, because the system or the solution we developed was fairly robot specific, at least on the execution side. So it would be nice to integrate with other robots that have ROS control interfaces. And then the other sort of like pie in the sky idea for now is the subject of safety certification. which is a whole can of worms, which is why we use the collaborative robot for all this research. But there's obviously a lot more than just collaborative robots out there, and this is a type of system which is not really robot dependent, so it would be useful if, and very exciting if we could use it on other robots that were not just collaborative rated. So that's about what I got. Any questions, thoughts, comments, kudos, criticisms?
No,
Hey,
Ben, I
Ben,
appreciate it.
it's Michael. I got a question about how did you represent the like human as in a collision object in your environment? So you just have kind of like the stick figure of the joints and, you know, like connections there, but how did you actually represent that in the collision environment?
Yeah, we basically just put like primitive collision objects on the positions of those joint centers that we figured out. So once we have that data, we took a few different approaches, and it's still an area of, you know, improvement that we have, is to get that model higher fidelity and higher reliability, because one of the problems that we encountered was noise in the data sort of interfering with the robot planning. In particular, it's pretty common for this motion planning or motion capture system to misjudge where an elbow is and maybe switch the left and the right elbows. So that can cause a lot of problems if you're trying to use like the relative positions of joints to do that representation. Mm-hmm. So we tried a few different ones, but basically just fitting primitives to the data that we had coming in.
Mm-hmm. Cool. And I think my other question was, so you mentioned like wanting to have a target minimum frequency for planning. Do you have any thoughts about like how you could achieve that minimum? Like what would you have to do to actually get to that 50 hertz minimum if you have plans that are taking longer?
Yeah, well, it's something that can't really be insured, at least on the hardware that we've got, just because sometimes the constraints that have been defined for a problem take longer to evaluate than others. And a lot of these longer plans that we saw here were ones where the robot had a longer distance to cover, so just a lot more states to evaluate. So, you know, one solution is to simplify and reduce the number of states that you're evaluating, but that's not always feasible. The easy sort of cop-out answer is get a better computer, because I recall in some of our early testing, Levi was able to do some of this upwards of like, you know, consistently, you know, with this peak at like 200 or 300 hertz. Mm-hmm. And there's other sort of parameters within the motion planning environment that can be tuned, like that longest valid segment, which kind of relates to the number of states you're evaluating in the planning process, mm-hmm. which has a pretty huge impact on the amount of time it takes for a plan to be evaluated.
Thanks.
Yep.
All right, cool. So, and a lot of the enhancements relative to the real-time motion planning can be found over in the Tesseract Robotics GitHub organization. So feel free to check that out. Right. So anyways, thanks, Ben. I appreciate it. Are there any other questions for Ben before I take over?
Can you hear me, Ben?
I can hear you.
Hey, did you by chance test any of the physics collision checking? I know it's about.
No, I didn't test any of that yet, but
okay.
Is that something that you?
It's 2.5 times faster than any of the others right now. So you would just get with the CPU implementation. So the GPU might be faster. So you just switching to that, you might get 2.5 times quicker planning or close to that just by switching to it.
Oh, cool. Yeah, maybe I'll give that a try real quick after the meeting.
So
thanks, Levi. All right. So I'm going to just plug the work we're doing on the hardware interfaces working group. So hopefully my screen is sharing. Zoom is acting really flaky today. But anyways, you'll notice I put it in parentheses, right? Because one of the things that's come up is that there is utility to have standard ways to interface with just non-ROS things, whether they be explicitly hardware or not, right? So, but in general, right? So this working group has now met twice, with the third meeting coming up actually this Thursday. So if that's something you're interested in learning more about, or wanting to see a more efficient means to enable non-ROS things to interact with ROS ecosystems, we welcome participation, right? So that being said, right, the goals are to come up with, obviously, notions of some best practices and process to drive potentially what we've been referring to as maybe a reference implementation, potentially reps, and as well as some other tools. Up front, we should probably be checking out some existing standards, particularly in the industrial realm, right? There's a number of different industrial standards. A lot of us from the world of industry have been exposed to some of those. And so it's been great working with some of those folks who've brought some of that background and experience. But more recently, in the discussions we've had to date, we've narrowed around a little bit more around some scope that we'll continuously revisit, and at some point create in the near future, basically like a little bit like formal sort of goal statements and scope. And there was a recent post on Discourse, right? So currently right now we're making posts about this over in the general section, where ROS working groups are communicating their meetings and what's going on, around even like, say, capturing something around functional safety, and how does that get implemented? How do you interact with, say, safety systems or processes that help govern safety in a consistent fashion, right? So there's been plenty of discussion. These notes are also available via the Google group that's been created. If you're interested, to shoot me a note, and I can get your email address added to the Google group and some of the other communication tools for the working group. So that's a little bit about the hardware working group, where we're actively meeting and working on addressing the state of interfacing with non-ROS things, if you will. And it's actually, all the meetings are also on the ROS2 calendar, by the way. So you can find the events that are now posted there. Any questions about the hardware working group? All right. Let me see if I can stop sharing. Excellent. So anyways, with that, I was going to make it a little bit of open forum time. I wanted time for folks that are here to voice, kind of like express their opinions about maybe some things that are of interest to see. So with that being said, let's open it up. Anyone want to either talk about what they're working on or area of interest? I'm also monitoring the chat, by the way, if you prefer the chat. All right. Michael, you made the notation about move it interface for Descartes Lite. I'm assuming, obviously, interfaces for move it are still of interest to the community. Is that something that we should be looking at?
Yeah, I mean, I think it's, to me, it seems valuable to continue supporting both. And I think, we can do a decent amount, I think, with the tools that we have to make them kind of available. But I know at least I have projects that leverage both Move It and Tesseract. And so I think, there's new stuff that happens in both of them, and I think they both kind of feed off of each other. So it seems kind of valuable to have that, and Move It just has a huge community and lots of things built on it. So I think being plugged into that community is a good thing for our tools.
Yeah, and good point, Michael. And obviously, we could potentially, like via the Move It maintainers meeting that Tiffany has been representing us on now, like raise that as well in that form, if that makes sense.
Right.
Anything else? Any questions from the audience? Feedback?
Not a question. This is Adam from Ohio State. I'd just wanted to vocalize. So like we're currently working through our own first implementation of a kind of motion planning pipeline using Descartes and trying to feed that in the trav job. So kind of what Michael talked about today was especially interesting to me. And, you know, as further documentation comes out on that, I think we'd definitely be interested in that as we're kind of exploring it ourselves now from what's out there. So.
Great. Thanks, Adam.
Yeah, that's a great point. I think a lot of the knowledge that we have about these things is kind of tribal and like, oh, just go read some of the examples. I think we could do a lot better in terms of like actually making documentation and, you know, writing some sort of like examples that go through and explain, you know, kind of like to John's question earlier, like why would you choose certain planners and how do you kind of go about setting that up? So that's a good point. That's something that we can try to focus on a little bit more, is like writing documentation that's valuable, that helps people kind of take these tools and understand at like a higher kind of not code level, how they work and how you kind of leverage them for different applications.
Excellent. That's a great comment, Adam. Thank you.
It's David Pietracola from Cohesive Robotics. Thanks for organizing today's meeting. Just want to throw out there, if anyone is working with ABB robots and ROS-II and trying to use the EGM interface for ABB, it didn't seem like there was a ROS-II package available yet in ROS Industrial. I think the one that ABB put out was for ROS-I, but it seems like Picnic Robotics just picked up kind of wrapping that EGM library. So we're looking to use that as well and then help expand it. So I don't know what their plan is to move that back over to ROS Industrial, but just wanted to throw it out there if anyone's working with ABB and their EGM interface.
Thanks for the heads up, David. I hadn't seen that.
Yeah, it's fairly new. I'll post their repo out here.
Sweet. Thanks. Just one other thing, if any of you that are based stateside are going to be in June in Detroit attending Automate, we are working with Picnic, Open Robotics, Canonical to organize like a roboticist meetup Wednesday night, co-located there with Automate. We're looking for something kind of a little bit not too far from the event center for Automate there in Detroit, but it's just going to be kind of like a network session. Roboticists can get together, you know, share some war stories, talk about like, hey, how's this Automate compared to other events, and maybe like, hey, an opportunity to kind of share what we're all working on. So stay tuned for that. We'll be communicating that as that gets pulled together across our communication channels. But, you know, just a FYI, like, right, we are organizing that with Picnic. It just reminded me. So we've been working closely with Picnic for some time, and thank them for all their contributions to ROS Industrial. If there's any closing comments, we are on the hour. I want to be respectful of everyone's time. But thank you, everybody, for coming. Don't hesitate either via discourse or hitting any of us up. If there's something you'd like to see, obviously, if you have something you want to share as well, this is the developers meeting, right? So by all means, those of you attending, if you have something you want to share or get feedback on, this is what the forum is for. So we welcome all the feedback and participation. We want to make sure that the open source contributions are reflective of the user needs and what the community is working on. So by all means, don't hesitate to reach out. You can always, you know, you can use Twitter. We're at ROS Industrial. We're on LinkedIn, of course, Discourse. There's a whole ROS Industrial channel or category on Discourse as well. So there's a number of ways to hit us up. So don't hesitate to reach out. If there's no other, I'll stay on the line if anyone has questions for me. But everyone, thank you for coming today. Michael and Ben, thanks for giving to speak. And then obviously we'll be seeing lots more of Michael in particular. He's kind of the lead of this particular meeting. I'm just always wanting to talk, I guess. So with that, thanks everybody. Like I said, I'll hang out as if anyone wants to stay and like ask a question or anything of me or something. Thanks.